My name is Luke Skyscraper, and today, I'm speaking with Maddy Moonfield, a scientist who's unafraid to dive, let's just say, into the deep. Maddy, let me start with a simple question. What do we actually see when we point our telescopes to the sky?
Those telescopes are really just an extension of our eyes. And eyes are nothing more than hypersensitive antennas that register photons. Your eyes may even detect a single photon, which is truly astonishing. A photon carries specific information, mainly its frequency, or wavelength if you will, which tells you how much energy it holds. All the eye really does is register that information and send it to the brain. It's only there, after a process of filtering and interpretation, that an image appears. A telescope works the same way. It gathers electromagnetic radiation.
You mean, like someone who's colorblind, they see the world differently because their eyes lack certain receptors? Is that what people mean when they say, reality doesn't exist?
Color is such a great example. It's nothing more than a specific wavelength in the electromagnetic spectrum, or rather, the part that's visible to the human eye, somewhere in the middle. The full range stretches from radioactive gamma rays, through visible light and infrared, all the way to low-frequency radio waves, with much less energy. But seeing a color is really a process, which is also why it's so prone to optical illusions. I'm not saying that objective, tangible reality doesn't exist. But from a philosophical perspective, what you perceive is a construction of the mind. And it's always something from the past, too. Because as you know, light takes time to reach your eyes.
Right, but in daily life that's mostly just theoretical, isn't it? Even though you can see the effect sometimes, like when there's a thunderstorm in the distance.
Of course. And if you don't trust your eyes, you can always take a closer look, maybe even touch it, or ask someone else if they saw the same thing. There's more than one way to verify information. Even if it's a planet far away, we can send a spacecraft to see it up close. Of course, making a call takes some time, with a lag of about 45 minutes if it's Jupiter, for example. But it's still doable. But what if you're looking at the Andromeda Nebula, our neighbor galaxy? Then you're seeing it as it was, 2.5 million years ago.
That does make things a bit trickier indeed. But that's what those instruments are for, right?
Exactly, and it's also one of the reasons for building ever more powerful telescopes. Because if we could look far enough, we might eventually observe the cosmic egg, that the universe hatched from. The question is, why is the speed of light what it is? Technically, it's a universal constant, the maximum speed for particles like photons that have no mass, traveling through a perfect vacuum. This vacuum has certain properties, like how it responds to electric and magnetic fields, and these are described by two other fixed numbers, the electric constant and the magnetic constant, or rather the vacuum permeability. It's something that we measure very precisely to use it in our equations, but we don't really know why it has that particular value. It's just a kind of universal speed limit. Because for objects that do have mass, faster than light travel simply isn't possible. Or rather, it would take infinite energy. Sure, you have warp drives and wormholes and so on, but it's not terribly realistic at all. And that makes me wonder, maybe that's the whole point. Maybe these values are deliberately set to, prevent us from taking a closer look.
I can see where you are aiming at. So how should I picture that?
Think of the screen of your laptop or smartphone. It can't be much smaller, right? It would be really hard to see anything at all. It's all about human proportions. But then, is there a limit in the other direction? Can a screen be too big? All that matters is the distance between you and the screen. A cinema screen is pretty large, because you're sitting a little further away from it. Now imagine something really big. I like to call it the world screen. It's a screen the size of a country, or state, hanging high in the sky, held in place by satellites or so. Of course it doesn't really exist, but let me go down that path for a moment. Think of something like a Dyson sphere. Not to generate energy, but to broadcast beautiful images and important news, for all to enjoy.
Sounds like a good science fiction story.
Doesn't it? Now let's take it one step further. Imagine we move our world screen way out, past Earth, far beyond the solar system. And it shows us exactly what we see when we look up at the night sky. Those magnificent galaxies, nebulae, supernovae, you name it. Here's the big, rather philosophical question. How can we be sure that what we're seeing are stars and galaxies made of atoms and particles, just like our own physical world? Or if it's just some kind of multidimensional display of truly outerworldly proportions?
That's truly bizarre. Are you saying that you don't trust your own eyes? I mean, your telescopes.
The problem is that basically, our theories don't match the observations. When we look at distant galaxies, they don't spin the way we'd expect. Based on the gravity of the visible matter alone, the outer stars should be flung out, but they're not. To explain this, dark matter was introduced. Not because it doesn't emit light, it's dark because we truly don't know what it is. As strange as that sounds, an even bigger mystery emerged, called dark energy, a force that pushes to expand the universe itself. It resembles Einstein's cosmological constant, a term he once added reluctantly to balance his equations. When Hubble discovered that the universe was expanding, it was dropped again. But in the 1990s it made a comeback, when new observations showed that the expansion is not slowing down as expected, it's speeding up. Today, we still don't know what dark energy really is, only that it seems to make up about 70% of the universe. Better telescopes and instruments have given us better data, but often they confirm the mismatch instead of closing the gap, between theory and observation. And so, we've now reached a point where this is widely referred to as a crisis in cosmology.
So what we're talking about here is the expansion of the universe, right?
Correct, and we can measure it in various ways. There's also a theoretical prediction, based on quantum field theory. But according to that, there should be far more dark energy than we actually observe. About 120 orders of magnitude more. That's an unimaginably huge mismatch. In fact, if that number were true, our universe wouldn't even exist. So, let's be thankful for that. As long as the measurements are consistent, right? Unfortunately, they're not. To know how fast the universe is expanding, we basically need to measure the distances between faraway objects, and how those distances change over time. But that's tricky. Think of seeing a plane in the sky. Is it large and far away, or just a little drone? In cosmology, we face the same challenge. So to estimate the distance to a faraway galaxy, we use what we call standard candles, objects with a known brightness. Type 1a supernovae are excellent for this, because they tend to explode in the same way, producing roughly the same amount of light. To calibrate these cosmic rulers, we use pulsating stars known as Cepheids, less bright but more common, and visible in nearby galaxies. Then there's the cosmic microwave background, leftover radiation from the Big Bang. You can even see it as static on an old cathode ray TV. A few % of that snow comes from the CMB. This provides us with information about the expansion of the universe as well. Here's the problem. The combined data suggest that the expansion of the universe is accelerating. But when we do our measurements, the numbers don't match up. The CMB gives an expansion rate of about 67, but the data we get from the Type 1a supernovae point to an expansion rate of about 74. It's like our cosmic bookkeeping doesn't balance. We even find stars that seem older than the universe itself.
But isn't that just a matter of gathering more data?
We're certainly trying. Since 2017, we've added something called standard sirens to our toolkit. These are gravitational waves from neutron star mergers, incredibly violent events that usually happen far outside our galaxy. These gravitational waves travel at the speed of light, so it's not the actual sound of sirens, of course. But when we combine those waves with the redshift measurements of these objects, we get a third estimate for dark energy. And it lands somewhere around 70, right in the middle.
The Three Musketeers of Dark Energy. Although in that story, there were four, right?
Lately I've been working on a fascinating project in Arizona, and this instrument is scanning the spectra of over 30 million galaxies and quasars, looking at their redshifts to figure out how fast different regions of the universe are moving away from us. Basically, what Hubble did in the 1930s, but at a whole new level. What's interesting is that some of the data we're seeing suggest that dark energy might not be constant after all. That idea's been floated before, but DES's measurements seem to hint at it. It's still very early days though, we can't say anything for sure yet. If it's true, it would mean that the accelerated expansion of the universe could slow down, and maybe even reverse. So instead of ending in a cold, empty big freeze, the universe might collapse back in on itself. You know, setting the stage for another roll of the cosmic dice.
You mean, like Roger Penrose's cyclical universe?
Exactly. His cyclic cosmology was always considered a bit speculative, but Roger Penrose did win a Nobel Prize in physics for his other work. He might be proven right on this point too.
They say that cosmologists make lots of mistakes, but they're never in doubt.
To be honest, we do sometimes forget to question our biggest assumptions. Like, when we see the universe expanding, we assume there's some force pushing from inside. But what if, just what if it's being pulled apart by something outside of it? I'm not saying that's what's happening. But if we never even want to consider the possibility, simply because cosmology says that there is nothing outside our space-time, then I don't think we're really being scientific, in a more philosophical sense at least.
Those constants you've been talking about, like the speed of light, is that what they mean by the fine-tuning of the universe? All those values that have to fall within extremely narrow ranges for atoms, stars, even life itself to exist. I mean, are we just incredibly lucky?
Everything is possible. But to me, it's like dropping a jigsaw puzzle and all the pieces land perfectly in place. Sure, it could happen, if you had an infinite number of tries. The way I look at it though, this kind of fine-tuning strongly hints at the existence of a multiverse. Maybe there's some kind of cosmic evolution process going on, where universes that support complexity and structure, like ours, are somehow more likely to survive. So, if we take a closer look at the Big Bang itself, well, we're really talking about cosmic inflation these days. That's the idea that in the tiniest fraction of a second after the Big Bang, the universe expanded at an absolutely staggering rate, faster than the speed of light. In this case that is allowed, because we're talking about space-time itself. This burst of inflation is what gave us the flat, smooth universe that we observe today. Again, the problem is that while this cosmic inflation is happening in the tiniest fraction of a second, it still has to twist itself into all sorts of corners to deliver the universe that we know. The theory may be a bit too flexible, and to be honest with you, it's starting to get a little ridiculous too.
For a politician it is quite common to bend reality to suit their agenda, isn't it? But scientists should know better, I suppose.
Absolutely. We should hold science to a higher standard. And to be clear, I don't claim to understand the true nature of the cosmos. In fact, part of the point is that maybe we can't know it fully, at least not just by measuring radiation and gravity. Not in the deeper, philosophical sense. Add to that the stress our best theories are under, already known as the crisis in cosmology, and I think that's when we should explore a wider terrain. So here's my question: what if the story isn't just about nature, but nurture too? What if these finely tuned parameters were the result of deliberate choices, made by some conscious agent, completely unknown to us? I'm talking about aliens, yes, but not the Hollywood kind. Not big-headed guys in silver suits. That was just how they dressed up an actor in the 1950s.
Are you saying the universe is conscious? I think that's an interesting idea, but not really cosmology, is it?
Personally, I don't believe the cosmos itself is conscious. For something like self-awareness, you need a body, a biological system capable of responding to stimuli, from outside and within. But I also don't think that consciousness is just a product of the brain. It's in every cell. The nervous system evolved to handle movement, not to produce consciousness, even if it plays an important role there as well. Because once an organism starts moving around through three-dimensional space, it needs a system to keep it from crashing into rocks or running off a cliff. That's what you have a brain for. It's a prediction device, to anticipate what's coming next and get you safely through the next second, or the next day, maybe even the rest of your life. And when that prediction suddenly fails, like when something startles you, the brain kicks in to very quickly recalculate. Even humor fits into that model. You know, something seems to go wrong. Your brain braces for impact, but then it turns out everything's fine. That sense of relief comes out as laughter, or at least a smile.
Okay, but memory, for example, isn't that mostly about remembering the past?
It is, but not just for remembering the good old days. Memory helps you predict. We need it to store all those experiences, so that when the moment comes, we'll hopefully get the right intuition, the right impulse, so to speak. But here's the thing. Our brains weren't designed to discover ultimate truths. They're built to keep us alive. And if a little story does the job, even if it's not totally accurate, your brain will go with it. That's one reason those myths and conspiracy theories you keep hearing can be so sticky.
Those are really cool observations. But where does that leave us? You were talking about conscious agents. Can you tell me more about that?
What I'm talking about isn't something like the Matrix. That's the popular image of living in a simulation, sure, but it's not what I mean. Our formulas and scientific models work incredibly well when it comes to the world of atoms and molecules. That's why we have all those marvelous apps, and Wi-Fi, and so on. We don't have to worry too much about living in a simulation if it doesn't change how we do physics or lead to new discoveries. What I mean is something more abstract, a kind of intelligence outside our space-time. Something that underlies it, or maybe even has full control over our space-time. Think of the world screen again. Now imagine a kind of multidimensional simulation, a riddle, wrapped in a mystery inside an enigma. Isn't that how Churchill once said it?
A multidimensional simulation? I've heard about the holographic principle. But that's more of a mathematical concept, isn't it?
It is indeed, and the research is still very much ongoing. But the basic idea is this. All the information inside a black hole, or maybe even the whole universe, could be encoded on its surface. Just like a hologram stores a 3D image on a 2D sheet. A black hole itself doesn't have a surface in the usual sense. It's a singularity, really just geometry, where the rules that govern space and time break down. So when we talk about the surface of a black hole, we really mean the event horizon, the point of no return beyond which nothing escapes, not even light. That's why it's called a black hole. And surprisingly, it turns out the black hole has a temperature. And it also has entropy, which means it contains information. Not tied to the volume inside the black hole, as you might expect, but to the surface area of the event horizon. So that's the holographic principle. It's fascinating, isn't it? Especially when you realize that this information is counted in tiny squares, each one a Planck area, the smallest possible pixel of space we know of.
In that view, is a higher dimension a projection from a lower one? Is that fair to say?
Think about how humans experience space. We mostly move around on a two-dimensional surface. We don't really navigate three-dimensional space. At least not in the way that fish or birds do. Imagine if we had access to even more dimensions, how different reality would be. Whether those exist, I can't say. On top of the 4 dimensions of spacetime, string theory needs 6 or 7 extra to work, but these are usually so tightly coiled that they escape detection. Still, this isn't just science fiction. Now imagine we're inside a deep simulation. It's one thing to show stunning images of galaxies and quasars on a giant screen. But how would you simulate things like gravitational waves? These have actually been measured here on Earth. When such a wave passes, even a yardstick stretches and contracts by an extremely tiny fraction. That's spacetime itself trembling. Then there's parallax, a method we've used since ancient times to measure depth. Your own eyes use it. Just look at your finger with one eye, then the other, and see it jump. Astronomers use the same principle to measure distances, but only for the nearest few 100,000 stars. And what about cosmic rays, highly energetic protons and other particles that bombard the atmosphere? Or how supernovae and magnetars forge elements like gold? Our models explain that remarkably well. We do see about 3 or 4 times less lithium than expected though. But don't worry, it's all in the game. The point is, to simulate all that would require total control over spacetime. And if that's possible, well, then anything is, right?
Speaking of anticipation, I'm sort of expecting the word quantum to pop up any moment. I'm joking of course, but seriously, where does quantum theory come in?
Quantum theory isn't just a buzzword. It began with the discovery that atoms don't absorb or emit energy continuously, but in sudden, specific jumps called quanta. Even light can't escape these rules. It's not just a wave, but made of photons, tiny packets of energy that act like both waves and particles. The famous double-slit experiment shows this beautifully. Fire a single photon at 2 slits, and it behaves like a wave, creating an interference pattern, as if it passes both slits at once. This strange in-between state is called superposition. But the moment you measure which slit the photon actually went through, the pattern vanishes. That's the collapse of the wave function, as scientists call it somewhat dramatically. It's like a burglar, let's call him Peter Photon, considering all paths into a house. As long as no one's watching, every option remains open. But in spite of his name, Peter is not all that bright. He gets caught on camera, and in that instant, only one path remains. Peter enters the registry, and from that moment on, his collapsed life is ruled by classical laws. But when all options were still open, the equations that described him were made for waves, not solid particles. Can poor Peter never escape his prison? Or might there be a way out, maybe a tiny quantum tunnel hidden behind a wall somewhere? He'd have to be very lucky, but photons, and even electrons, do it all the time. In fact, plants rely on this bizarre quantum tunneling effect to harvest sunlight with incredible efficiency. So don't try human-splaining to Mother Nature how quantum physics works. As you might imagine, that kind of unpredictable behavior brings quite a bit of uncertainty. So how do physicists handle that? Easy, just call it a principle. The uncertainty principle says that in the quantum world, there is only so much information you can get from observing a particle before its wave function collapses. By the way, the observer doesn't have to be a person. Any interaction that transfers information can count. Even a subatomic particle will do. But what if there's no observer at all? Think of the Big Bang. Could that have been the collapse of a colossal primordial wave function? And if so, what, or who did the observing?
I did an interview a while ago with Seth Lloyd, and he said that fundamentally, Everything is information. And that basically, the universe is a giant quantum computer.
Fascinating. In physics, information means anything that distinguishes one state from another. In that broader sense, yes, everything is information. That said, if the universe is a giant quantum computer, then maybe black holes serve as the qubits. A classical bit can only be a 1 or a 0, but a qubit can be in any superposition of both. In actual quantum computers, those qubits can be anything, from photons to ionized atoms or to circuits that act like quantum particles. To keep their fragile properties alive, these quantum systems have to be cooled to near absolute zero. A black hole is even colder, but what makes black holes especially interesting is that their surfaces, or rather event horizons, hold the highest information density we know of. And it gets even weirder. Some physicists believe that two black holes could be entangled, at least in theory. If so, they might be connected by a kind of shortcut through space and time. Even a traversable wormhole becomes conceivable. But don't get too excited. To open such a portal, you'd need an exotic kind of fuel to produce negative energy, something with negative mass. It exists in our equations, sure, but not in any practical way, shape, or form. At the opposite scale, entangled subatomic particles might also be connected, not by space tunnels, but by a deeper geometry in spacetime. No matter the distance, whether a few miles, or even light years, if two photons were once part of the same system, then measuring one instantly affects the other. You could say their information is entangled. So if Peter Photon were still entangled with his friend outside prison, anything that happened to one would instantly reveal the state of the other. Sadly though, they still can't send secret messages faster than light. Even so, quantum communication networks are already being built that use this kind of entanglement for perfect security. What makes those useful is that any attempt to intercept a message is instantly noticed. But to me, they also hint at the possibility that an entire simulated universe could be running completely undetectable.
We're running out of time. Although from what I hear, at the quantum level time doesn't even exist. Is that true?
There's an ancient Indian textbook on astronomy, nearly 2,000 years old, that already describes time as having two aspects, formed and formless. In a way, that mirrors the two major concepts of time in modern physics. First, there's relativistic time, a dimension of space-time, shaped and stretched by gravity. In fact, GPS satellites in orbit experience weaker gravity, so their clocks need continuous correction. Or else your GPS would be off by several miles, after just one day. Due to the laws of thermodynamics and the increase of entropy, relativistic time has an arrow, pointing in only one direction. You could think of this as the formed aspect of time, measurable, and woven into the fabric of the universe. Then there's time in quantum mechanics, ticking in the background, but not really part of the system. The equations of quantum theory are time-symmetric. They work just as well forwards as backwards. This is time's formless face, elusive, untouched by gravity or space-time. These two concepts of time are deeply incompatible. That's one of the reasons why it's so difficult to unify general relativity with quantum mechanics into a model, known as quantum gravity. One solution is to remove time from the equations altogether, and that's probably where the idea comes from that time might not exist at all. I think time does exist, but in multiple ways. There's a third aspect of time in that old text I mentioned. It says, "Time is the destroyer of worlds." Entropy again, but here, it essentially means death. In my view, the passing of moments and the memory of events, the awareness of time as we perceive it, is an essential part of consciousness. I often say, don't count your life in days or years. Count it in experiences. Because it's the moments that stretch time in memory, that looking back, will give you more lifetime. So let's go gather new experiences. Why not visit a whole other universe? Just be warned, not just the time zone, but time itself could be totally different. We usually assume the laws of nature are the same everywhere. But even within our own universe, that's not guaranteed. Imagine how in another universe, the equations might be wildly different. That's how, from the perspective of such a universe, our spacetime might be something perfectly controllable, to be manipulated and played with, like a cosmic video game.
But why? That's the only question I have. What would the motives be for building such a big simulation?
Maybe someone just wanted to create something beautiful. It certainly is a masterpiece, this universe we live in. But I suspect there must be a deeper motive for building such a vast, complicated structure. Of course, at any given moment, only a small part of time and space needs to be rendered. You know, like your GPS doesn't show the whole city in full detail, only the part you're driving through. We've been talking about dark energy, that ghostly force that causes the universe to expand at an ever-increasing rate. That means new spacetime is being created constantly. But where does all that extra spacetime come from? Is that new information? Like this interview just kept expanding? Some say the foundation of reality is a kind of quantum foam, like a cosmic mattress for the universe to rest on. Even in a perfect vacuum, absolute emptiness, there are still quantum fields, and short-lived pairs of particles popping in and out of existence. Like yin and yang, pairs of opposites inside the eternal circle of being. In my view, if you could travel far enough into the universe, you'd find it's not that big at all. What you'd encounter is an impenetrable wall of increasing information density that you're not supposed to discover. You know, the world screen. A multidimensional simulation that generates not just all those photons we catch with our telescopes, but all other particles too, and even Earth-shaking events like gravitational waves. Then again, it's more likely you just find more stars and galaxies made of rock and gas, maybe dark matter too, until you finally loop back to the point where you started from. I'm not trying to put humanity back at the center of the universe. It's also not my intention to sneak in a proof for the existence of God. I don't pretend to know what the nature of the cosmos is. Perhaps the development of intelligence is somehow a purpose, who knows, to combat the devastating arrow of time. Many people think that before we had telescopes, everyone believed the Earth was flat. But that's not the case. The ancient Greek philosophers were for the most part convinced that Earth was a sphere. They just didn't have the tools to prove it. Who knows where we'll end up? With the development of quantum webs and AI, or something else entirely. But until then, it won't do any harm to map the terra incognita already, even if we have to add a few dragons here and there.